We're now going to consider how to solve some problems using Newton's laws of motion. The first problem we're going to consider is the problem of a block sitting on a ramp. The block will be moving up the ramp, but there will also be friction between the block and the ramp. We'll be given both the static and the kinetic coefficient frictions. And we'll know what the initial velocity of the block has at the bottom of the ramp. What we're going to look for is what is the acceleration of the block and how far up the ramp will the block slide before it stops. And we will simply assume the ramp is long enough, so you don't need to worry about the block sliding so far it falls off the edge. We're going to solve this problem using the exact procedure we set out before. We're going to start by drawing the free body diagram. With these are the forces we're going to consider. We're going to pick a frame of reference, and it must be an inertial one. And then we're going to apply F equals ma, in this case to only one object. And then we're going to apply the constraints and force laws. This will give us a set of equations which we will solve to then find out the answers. So first, free body diagram. So here are our forces, and here's our objects. So what I want you to do is we'll pause the video, take a stab at drawing the free body diagram, then we'll go over it. So, first, we don't need to worry about air resistance. We will assume that this velocity is small enough that we don't need to worry about air resistance. In addition, again, we're not given any information to calculate air resistance. We also don't need to worry about any tensional forces because there are no ropes or cords or anything attached to the block that is moving. We do need to worry about weight. That's vertically down, equal to mg. We do have a normal force, which is perpendicular to the surface. So in this case, that means it's up at an angle, not straight up opposite weight. And we have friction, and friction always opposes the velocity. So velocity is up the ramp, friction is down the ramp. In addition, this friction will have to be kinetic friction because the block is moving. So those are our forces. We now need to pick an inertial frame of reference. First, we could put our frame of reference, as we usually do, x be horizontal and y be vertical. But that would mean the block would have both x and y components for its acceleration. It'll be easier if we simply take those axes and just align them with the ramp. If I make the axis directly up the ramp, then the acceleration will have no y component because the ramp will constrain the block to move straight up in this direction along the x-axis. So what we're going to do is tilt our axes along the ramp, and that's the set of coordinates we're going to use. We're going to attach it to the ramp will be stationary, this will be an inertial frame of reference. With that set, next thing we're going to do is consider some geometry, because the angle we are given is the angle that the ramp makes, which is this angle right here. If we put our x and y axes along and perpendicular to the ramp, the weight will not be in the y direction. So we're going to have to break the weight into its x and y components. To do that, we're going to need the angle between the weight vector and the y-axis or the x-axis. That's not the angle we're given. But with a little bit of geometry, we can calculate it. This right here is perpendicular to the ramp because that's the direction of the y-axis. This is a right angle. If this is angle theta, this angle right here must be 90 degrees minus theta because these two must add up to 90 degrees. Now, in addition, this right here is a right angle because gravity acts vertically down. This is the horizontal angle, the horizontal line, so therefore this has to be a right angle, which means this angle and this angle must add up to 90 degrees, so that this angle must also be theta. So with a little bit of geometry, we find out this angle right here. So when we redraw our original graph, we have this angle right here is theta. That allows us to break the weight vector into its x component, which will be mg times sine theta, because this is the side opposite the angle, and the y component right here will be mg cosine theta, because this is the side adjacent. So that allows us to break the weight vector into its two components. With that having been done, we need to write down F equals ma for the block. What I want you to do is take a stab at doing that, and then we'll go over it. Now, in the x direction, we're just going to read off the forces we have that have x components. We have this component of gravity, which is acting along the negative direction, because our x-axis points up the ramp, so this is the negative direction, so that's minus mg sine theta, this right here, and friction acts in the same direction. Again, it's negative, minus f, and that equals m times a. The acceleration has only an x component, so we don't need to put a subscript on it. In the y direction, we just have the normal force, which acts up along the y-axis, and mg cosine theta, which acts along the negative y-axis, so it's got a minus sign right there. And the block will not be moving along the y direction, so the acceleration there must be 0. So those are our two equations from F equals ma. Next thing we need to do is apply constraints and our force laws. Well, the one thing we need to worry about is friction. The block will be moving, so friction will be kinetic, and the frictional force therefore will be the coefficient of friction times the normal force. And remember, it's the normal force. Don't write down the weight, because the normal force is the force that determines friction. Now we just take all of these equations and we collect them together. So we've got this equation from Newton's second law, this equation from Newton's second law, and our force law for friction. To solve these, first we'll solve this one to get the normal force. Note the normal force is not the weight. It's mg times the cosine of theta. It is less than the weight. That tells me the frictional force with a coefficient times the normal force, which is mu g times cosine theta. Take this, plug it back into the first equation up here, and we solve that for a, and the acceleration is minus, because everything here is negative, g times the sine of theta plus mu cosine theta. That's part of the problem. We wanted to find the acceleration of the block, and there we have it. Next thing we need to do is find out how far the block slides before it stops. Well, that will be a kinematics problem. What we know is the initial velocity, the v0 we were given. We just calculated the acceleration using Newton's second law, and we want to find out where its velocity is 0. And what we're looking for is the displacement, and we want to find out where that velocity goes to 0. Here are our kinematics equations. So what I want you to do is figure out which one of those kinematics equations should we be using to find the displacement. Pick that from the question that will be popping up. Now, the equation that's probably best to use is this third one right here, because all the others have time in it, and we don't know time, and we're not asked to find time, so therefore, look for the equation that does not include that, which is the third one. In this equation, we do know the initial velocity. We were given that. We were looking for where the final velocity goes to 0, so we know that. We also calculated the acceleration, so we know that. And the displacement is what we want to find, so we solve this equation, and that's our final answer. This is the distance that it'll move. So before we leave, we should first ask the question, okay, do we have the correct units? So let's go back and look at the equation for acceleration, which is this one right here, and it should have units of acceleration. Well, here we have g, which is meters per second squared. Sine of theta is dimensionless, mu is dimensionless, cosine theta is dimensionless. So this expression does in fact have the correct units. So let's go back and see, does the expression make any sense? Well, the acceleration is negative, which is correct. It should be slowing down and stopping. And note here, it'll be negative because both friction and gravity are acting in the same direction to slow down the block. And therefore, both of them should be contributed to slowing it down, which is what our expression shows. So our answer should make some degree of sense. So we're done.